Chapter 4, Phosphine ligand. Phosphine PR3 has a structure of pyramid trigonal as geometry and as figure of repulsion tetrahedral, where we have three groups R linked to P and lone pair in the orbital of P. The type of hybridization in PR3 is sp3. So phosphine by theory are donor 2 electrons terminal. The nature of the R groups affect the donation of phosphine. If R groups are good sigma donor to phosphine, it will increase the electron density on P, and therefore PR3 is more donor. Another factor in the phosphine is the steric effect of the R groups. When R is bulky group or PR3 is bulky ligand, in this case the donation from phosphorus will be weak. So the nature of the group R has effects on the donor acceptor property of the phosphine, and I will explain later what is the acceptor property of phosphine. Phosphine are important class of ligands. Their electronic and steric property can be predictable over a very wide range by varying the R groups. Phosphine is one of the most important ligand in organometallic chemistry because phosphine is a moderate donor, so it can be bound to the metal then released. And if we want, for example, if we have in the organometallic complex a vacant site and we are afraid that this vacant site will be occupied by the solvent or other ligands in the reaction, so we can add bulky phosphine. Bulky phosphine is bound to this vacant site, but the bond is weak due to the steric effect of this ligand. So at any time we want to remove a phosphine, we can replace it by another ligand, L'. For this reason, the phosphine got their importance. They can stabilize the metal complex R3PNML because phosphine will increase the electron density on M. And as I said, phosphine can be released easily from the organometallic complex, so phosphine are spectator ligands rather than actor ligands. Phosphine is bound to the metal M by the lone pair, so phosphine is a neutral ligand 2 electron donor. And by theory, phosphine may be pi acceptor of electrons of metal to the orbitals around P. The nature of the R groups affect the donation and the acceptance of phosphine. When R groups are good donor, it will increase the electron density of phosphine, so PR3 become more donor. And if R group are electron withdrawing, and if the metal bound to phosphine is rich in electrons, we will have back donation from the metal M to the orbital of phosphine. In case of CO, we saw that the back donation from M to the CO occurs in the orbital pi star. So what is the orbital of acceptance of phosphine? Consider, for example, the bond Px, and X is chlorine, so P and by P3 and Cl by P5. So we have to fill 8 electrons in the molecular orbitals of Px. Sigma P, pi X, pi Y, pi X star, pi Y star, 2, 4, 6, 7, 8. The highest occupied molecular orbital in Px is pi star, and the lowest unoccupied molecular orbital is sigma star. So Px can receive electrons in sigma star P. If sigma star P has higher energy, it would not become stable, so it cannot receive electrons. As X is more electronegative, like this Cl, the energy of sigma star P will decrease. So sigma star will be low enough in energy to act as a good acceptor orbital for interacting with d orbitals on metal. So phosphine is always sigma donor. Phosphine ligand is pi acceptor if the R groups around P has high electronegativity. So by theory, in this case, it can receive. We have another condition to have back donation from the metal to this vacant site is that metal will be rich in electron density. So the back donation has two conditions. First, we will have on the ligand an orbital to accept electrons, and second, the metal should be rich in electron density. Comparing phosphines and amines ligand. Like NR3, like amines, phosphine have a lone pair on the central atom that can be donated to a metal. But phosphines are more sigma donor than amines. And like amines, phosphine are also pi acceptor. Amines are not pi acceptor, but phosphine might be pi acceptor, and this pi acceptance depends on the nature of the R groups around phosphine. For alkyl phosphines, the pi acidity is weak since the alkyl is a stronger donor to P. So alkyl phosphine are good sigma donor, but they have low pi acceptance. Aryl, dialkyl amino, and alkoxy groups are more effective in promoting the pi acceptance or the pi acidity due to the presence of other Lewis base atom, which is nitrogen in the dialkyl amino and oxygen in the alkoxy group. PF3 is the strongest pi acceptor in the family of phosphines, since F is the most electronegative element in the periodic table, so PF3 is the weakest sigma donor and the strongest pi acceptor, and its pi acidity becomes as great as found for CO. In case of carbonyl, the acceptance from the metal to this ligand occurs in the orbital antibonding pi star. So the pi back donation in case of carbonyl will increase or will strengthen the bond MC and will destabilize the bond in carbonyl, since the bond order in case of CO decrease. By the same way, the acceptor orbital in phosphine is sigma star. So the back donation from metal to phosphine will weaken the bonds in phosphine. According to this order that is found experimentally, the weakest pi acceptor is p-methyl-3 and the strongest pi acceptor is pH3. Or by other word, the strongest donor is p-methyl-3 and the weakest donor in the family of phosphine ligands is PF3. Phosphine ligand donation is affected by two factors: the nature of the R groups around P, or the donation of the R groups, and second, the steric effect or the bulkiness of the phosphine ligand. In 1977, Chad Tolman, working for DuPont Chemical, did a classic review article. He studied a variety of phosphine ligands in terms of their electron donating ability and steric bulkiness. To remember that R group donor phosphine is more donor, and if the R groups are bulky groups, so we have a steric effect, and in this case the phosphine would not be a good donor and the bond M-phosphine will not be stable. So we have two factors to study always in phosphine. The experiment done by Tolman, several phosphine reacted with the nickel carbonyl complex to give NeCO3 plus CO. So we have one phosphine that replaces carbonyl. And he changed the nature of PR3 and studied the mu-CO in infrared analysis of this complex. So, as PR3 is more donor ligand, it will increase the electron density around nickel, and the pi back donation from nickel to CO increase, so mu-CO will decrease. So as phosphine is more donor, we will observe lower mu-CO. The second important feature of phosphine as a ligand is, as we said, the variable steric size, which can be adjusted by changing the R groups. CO is so small that as many can bind as are needed to achieve 8 electrons. And we saw, for example, for some complexes, we have 7 carbonyl ligands around. In contrast, the same is rarely true for phosphine, where only a certain number of phosphines can fit around the metal. This can be of great advantage is that by using bulky phosphine, we can favor forming lower coordinate metal, or if we have a room vacant around the metal M, it can be used by this bulky phosphine, and when you want to add a ligand, it can replace simply this bulky phosphine. So we can say in organometallic chemistry that bulky phosphine are well-leaving group of the organometallic complex. The usual maximum number of phosphine that can bind to a single metal is, for example, in general, we have exceptions, is 2 for the phosphine cyclohexyl 3 or phosphine isopropyl 3, and we have 3 or 4 triphenylphosphine around a metal. We can have up to 6 p-methyl 3 around the metal. Consider, for example, this complex, which is the palladium phosphine bis tertiobutyl phenyl. As we observed by X-rays, these phosphines are bulky, are very bulky group, are a stellic group. So palladium can have only 2 types of this ligand. And this ligand is not 18 electrons complex. So it can receive more ligands phosphine. But due to the presence of this bulky group, it will prevent the addition of other coordinating ligand to phosphine, to palladium. Return to Tolman's cone angle. The cone angle, according to Tolman, is obtained by taking a space-filling model of MPR3 group. MPR3 group, and this angle theta is the Tolman angle. The cone that will just contain all the ligand when the apex of the cone is the metal. So this angle theta, or by other way, we can take this ligand and the angle theta will be from this side. Although the procedure may look rather approximate, the angles obtained have been very successful to explain the behavior of a wide variety of complex. What does it mean? According to Tolman, as theta increase, that means the phosphinic group is bulky. And the result, the M phosphine would not be stable, and M release this bulky phosphine easily. The problem will occur when R groups around P are good donor and the phosphine is bulky. If R groups are good donor, it will increase the electron density around P, so P is more donor to M, and in this case, MP is more stable. But the phosphine is bulky, so angle theta is great. That makes this phosphine unstable ligand to M. So we have two opposite factors. R donor, the phosphine is better donor, MP is more stable, but the phosphine is bulky, so M phosphine is less stable. So we have two opposite factors. We will see and we will admit that the effect of the steric bulkiness or the steric effect is more important than the effect of the donation of the R group. According to Tolman theory, in the complex NiPr3CO3, when Pr3 is more donor to Ni, the back donation from Ni to CO will increase, so μCO will decrease. The lowest CO stretching frequency means the most donating phosphine. Now, how to study the donation of the phosphine? If the R groups are donor to P, Pr3 is more donor. And if the R groups are bulky, so Pr3 is less donor to Ni. Tolman studied the variation of the μCO in this complex according to the Tolman angle theta for several ligands phosphine. From p-butyl-3 to p-O-isopropyl-3, the two ligands are bulky. So the effect of the bulkiness is not present in this case. But p-butyl-3 is more donor than p-O-isopropyl-3 due to the presence of the electronegative oxygen. So p-butyl-3 is more donor than this ligand. So μCO in case of p-butyl-3 will be less than in case of p-O-isopropyl-3. So comparing p-methyl-3 and p-tollyl-3, p-methyl-3 and p-tollyl-3 are good sigma donor, but p-tollyl-3 is bulkier than p-methyl-3. For this reason, p-methyl-3 is a stronger donor than p-tollyl-3, and μCO is less. Here we have the common phosphine ligands. Triphenylphosphine is of medium donation. The best sigma donor phosphine are p-methylphenyl-2, p-methyl-2-phenyl. P-tertiary-butyl-3 is a good sigma donor, but pay attention, is a bulky group. So the alkyl phosphines in general are strong donors. The poor sigma donor, the good pi acceptor, like PO-methyl-3, PO-ethyl-3, and PO-phenyl-3, to remember that PF3 is the weakest donor ligand in phosphine family and the strongest pi acceptor. Here the structures of some polydentate phosphines. In general, polydentate phosphines are good sigma donor, and when they are bound to the metal center, the bond is always stable. Some structural issues about phosphines. When we have two phosphines in a complex, they tend to have a transposition to one another in order to minimize the steric interactions, especially for bulky phosphines. Chelatic biphosphine prefer the cis geometries. Two electron-rich metal will generally not want to have a strong electron donor alkylated phosphine. So it will lead to weaker MP bond and more likely phosphine dissociation. The MP bond is stronger for alkylated phosphine and for metals poor in electron density. The alkylated phosphine are very good sigma donor. They will strengthen the bond between M and P due to the overlap of orbitals, and the metals that are poor in electron density will pump the maximum donation density from the phosphines. As we said before, when the phosphine ligands are more donor, that means the bond MP is stronger and the bond distance is shorter. But the experiment proved that we have some exceptions. For example, consider the two complexes, chromium CO5 PCl3 and the chromium CO5 p-methyl3. By theory, the p-methyl3 is a stronger donor than PCl3 due to the presence of the donor group methyl in p-methyl3 and the electron withdrawing group Cl in PCl3. So the bond chromium p-methyl3 should be stronger than the bond chromium PCl3, and therefore chromium p-methyl3 bond distance should be shorter than chromium PCl3. And the donation capacity of p-methyl3 and PCl3 was proved also by DFT calculation, density functional theory, that measure the electron density around all atoms in the ligand. And this DFT calculation proved that the highest occupied molecular orbital in case of PCl3 equal minus 8.36 electron volt, and in case of p-methyl3 minus 6.23 electron volt. That means in p-methyl3 we have higher energy orbital, so it's better sigma donor and therefore greater orbital extent of the p-lone pair on p-methyl3. But the experimental results of Aroney and co-workers in 1995 proved the inverse. The bond chromium p-methyl3 bond distance is greater than Cl-p-Cl3. They explained this by the strong pi bonding in case of PCl3. The presence of chlorine, which of high electronegativity, make PCl3 a stronger pi acceptor. So the back donation in chromium PCl3 is greater, and therefore chromium PCl3 is shorter. So as a general conclusion, when the ligand is a stronger donor, the bond M ligand is stronger and this bond is shorter. But for some metal ligand complexes, we can have some exceptions proved by the experiment, like in the example of chromium CO5 PCl3 and the chromium CO5 p-methyl3. This exception was explained by the strong pi acceptance of PCl3 with respect to p-methyl3 that makes the back donation from chromium to PCl3 stronger than from chromium to p-methyl3. The most important technique to identify carbonyl complexes is the infrared, where we measure the stretching frequency of CO. The best technique to characterize the phosphine complexes is the phosphorus NMR. The typical chemical shift region for hydrogen NMR spans about 20 ppm, but in case of phosphorus NMR, it can span almost 1000 ppm, including the phosphide ligands.